Hi, and welcome to our next section, Acquiring Forensic Images. In this section, we introduce some fundamental concepts about forensic imaging and then cover two command line tools, DCFLDD and DC3DD, and a graphical user interface program, GuiMaker, designed to acquire forensic images. Now we move on to the first video of this section that deals with a brief introduction to forensic imaging. In this video, we explain hardware and software write-blocking techniques, the various forensic image formats, and hard disk physical structure and geometry, together with special ATA features that are relevant for digital forensics, mainly the device configuration orderly and their host-protected area. Forensic image acquisition could be defined as the process of acquiring a forensically sound copy or image of the device or media to analyze. The image shall be forensically sound. That is, we'll be able to verify that it's really an exact copy of the original and that the procedure to acquire it is well documented. The forensic imaging phase is very important in the digital forensic process because the acquired image file is the basis from which examiners extract and analyze data to find the evidence. So, if the image is not acquired correctly, all the subsequent work is in vain. Technically speaking, a forensic image is a bit-by-bit copy of the media to acquire. It differs from a single clone of the file system as it's a copy of all the raw sectors of the disk or partition. When acquiring an image, it must be ensured that no writes are made at all to the original media. Moreover, we must use cryptographic hashing to verify the integrity of the image, and any input-output errors must be logged, as prescribed by the NIST Computer Forensic Tool Testing Program. Before collecting any drives or media to be analyzed, it's a good practice to take photos and notes about them as well as the scene and suspect's computer. In this and the following video, we refer to imaging of a hard disk. We refer to the imaging of a hard disk as it's still the most common case when dealing with desktop computers and laptops. There are basically two scenarios when it comes to acquiring a forensic image. First is when the hard drive is not removed, and second is when removed from the suspect's computer. In the first case, which has a beautiful example when a hard drive could not be physically removed or during incident response, we must use a forensic live CD, like Kali Linux, to acquire an image. A live CD shall be booted to the so-called forensic mode that prevents the OS from automatically mounting any attached drives and does not make use of the swap partition when booting. If you want more information about the Kali Linux forensic mode, refer to the official documentation on the Kali Linux website. In the second case, when their drive is being removed, we must physically attach it to the forensic workstation using a write-blocking mechanism. Write-blocking mechanisms can be implemented both in hardware and software. Hardware write blockers are devices used to connect the drive to the forensic workstation that block any write attempts from the operating system to the drive. We could have various types of connectors to deal with different types of drives. Hardware and blockers are usually quite expensive, but their use is recommended because they are more reliable than software write block techniques. An example of a hardware write block is shown in this photo, with a hard disk attached through the SATA connector. Software write blocking is quite a controversial topic. Indeed, simply mounting a drive on Linux as read-only does not guarantee against possible writes that kernel drivers could make to the device. To solve this issue, various techniques have been developed. The most effective one is a solution based on a kernel patch that blocks the write commands issued to the drive at the device driver level, so at the software lowest level. As it's a kernel patch, the drawback is that we have to recompile the kernel to apply it. For more information about this patch, refer to this link on GitHub. We've seen that in the image acquisition process, all the bytes of a disk are copied into an image file. There are different forensic image file formats. Most common in an open source forensics is the raw image that is a mere duplicate of all sectors of a hard disk. Raw images contain no additional metadata, apart from most of the file systems, unlike the other forensic formats. We're going to use this format during the course. Raw images can be obtained with tools like DD, data dump, which copy stream of bytes from the input source drive to the output destination file. The limitation of DD is it lacks certain features that are required for forensics, such as cryptographic hashing and error handling. And logging. In the next video, we're going to see some variants of DD, specifically designed for forensics. Another open source forensic format is the Advanced Forensic Format created by S. Garfinkel. This format supports compression and encryption of the images and a software package called AFFlib. It's been developed to convert and manage AFF images. There are also proprietary formats. Most important are the Expert Witness format, used by software Encase, and Smart, used by FTK. Both support compression and encryption of images. And about the Expert Witness format, an open source library and related tools have been created to convert and manage EWF images. Before proceeding to the hands-on part, it's useful to recall the hard disk physical and logical addressing. Hard disk is formed by various platters, each having two heads. Each having two heads that read and write data on its sides. Each side is subdivided into many concentric circular strips, called tracks. All the corresponding tracks aligned through the stack of platters form a cylinder. Each track is subdivided into units called sectors. A sector is the smallest addressable disk unit. Traditionally, sector size is 512 bytes, but newer disks have moved to the advanced format 4KN, where the sector size is 4,000 bytes, though still providing 512 byte sector emulation. Traditionally, physical blocks or sectors are located using the cylinder head sector addressing scheme. Though it's now outdated and replaced by logical block addressing, it's still used to specify the hard disk geometry. Logical block addressing scheme is a linear addressing scheme where sectors are located by 48 bits integer indexes. Integer indexes. There's also a formula to convert the CHS addresses to LBA addresses. In this picture, we can see an example of why a disk geometry specified in cylinder head sector together with the number of LBA sectors available. There are two features that are unknown to the majority of the users, but are very important for a digital investigation: the device configuration overlay and host protected area. Device configuration overlay was introduced in the ATA6 standard to allow vendors to configure reported disk capacity and features. Host protected area was introduced in ATA4 standard to hide certain portions of the disk to an operating system and reserve them to store, for example, recovery data and so on. While designed and used for legitimate purposes, these features have also been abused to store and hide malware and any kind of illicit data. Both device configuration overlay and host protected area could be detected and removed using a tool called HDPARM. Now we're going to briefly show its usage. Suppose that the target disk has been attached to the forensic workstation. On Linux, hard disks identified by block device files under the dev directory in the format, for example, /dev/sdax, std, stc, etc. Suppose our disk is identified by sda1. To have more information about the disk, we can run the command hdparm. In it, we can see information like the model number, serial number, firmware revision, number of cylinders, heads, and sectors. Also the LBA user addressable sectors, and scrolling down, the device configuration overlay feature set. To see more info on device configuration overlay, we can use the command It shows, for example, the host protected area is set on the disk. There's another option of the HDPARM tool that allows us to see more information about the host protected area set, on the disk, and it's the N option. #HDPARM-N/dev/SDA. We can see that the host protected area is enabled on the disk, and the first number is the maximum number of sectors that are visible to the operating system, while the second number is the total real number of sectors on the disk. So the difference between the two numbers are the number of sectors that are hidden between the operating system and so to the user, but are used to store our kind of data. To remove the hosted protected area, we can issue the command with the same option and followed by the total number of sectors of the disk. And this command is to set the total number of sectors available to the operating system to be real total number of sectors. and so disabling the host protected area and allowing us to acquire the total real numbers of sectors. The total real number of sectors, that is, the full capacity of the disk. So we type the total number of sectors here. To make this change permanent to the reboot, we must prepend the number with letter P. Now we can see in the output that the number of sectors visible to the OS is equal to the number of real sectors available in the disk, and the host protected area has been disabled. In this video, we've talked about the fundamentals of forensic imaging, covered the topics such as hardware and software write blocking, different forensic image formats, disk geometry, and its special features, DCO and HPA, and how to practically remove them. Very good. In the next video, we're going to introduce two command line tools specifically designed for forensic acquisition, DCFLDD and DC3DD.